Section 3.2, Rolle's theorem and the mean value theorem. Last time we had gotten to the point where we had just briefly introduced the mean value theorem. We talked about the fact that it is a more generalized case of Rolle's theorem. And in fact, if we actually let f of a and f of b equal each other, which is one of the conditions in Rolle's theorem, then this formula, f prime of c equals this ratio, actually becomes equal to 0, and it turns into Rolle's theorem. So if we have that condition, that extra condition on there, we actually have the mean value theorem. With this one extra condition, we have Rolle's theorem. We talked about visually what this looked like, and we even gave an example in real life about how police officers can use this to determine speed. So we're going to do some examples next. We're going to determine whether the mean value theorem can be applied, just like we were determining whether Rolle's theorem can be applied. And if it can't, of course, we're done. Yay. If it can, then we have to go through the next steps, which is to take the derivative and then to also do this ratio and find out where they're equal. So the if it can be applied is actually a little bit more work. Not a lot, but it's a little bit more work than Rolle's theorem. All right, so we have a function, f of x equals x squared. There were two conditions over here for us to check for the mean value theorem. What are they? Yeah, continuous and differentiable. And is this function continuous and differentiable?
Yes.
Yes, why?
Because it's a polynomial.
Yeah, it's because it's a polynomial. We get these for free, almost, pretty much, because it's a polynomial. Okay? And I expect that you're going to write that down for me. That's how I know that you checked it. All right? I have no way of knowing if you don't actually write down that you did it. All right, so mean value theorem will be able to be applied. So mean value theorem applies. We will be able to do this ratio back over here that we talked about. Oh, actually, I think it was on here too. Okay, so there's two sides of this ratio, or this equation. The left-hand side is a derivative. The right-hand side is a ratio, or a slope. So we're going to calculate two different things. We'll start with the left-hand side because it's the calculus side. What is the derivative of this function, f of x equals x squared? 2x. Absolutely. So, and if we plug in c, we can. I mean, if you want to, it's not a big deal, but we could write that this is 2c. Fine. The right-hand side is to calculate f of b minus f of a over b minus a. What in the world are b and a? Yeah, they're the endpoints we were given, and in this function it's -2 and 1. And it doesn't matter the order, just as long as the numerator and the denominator's order matches. So usually we go with the second one, which is the larger one, in this case 1 first, and would be 1 on the bottom. And we have the smaller one, which is the -2 second, and then -2 on bottom. Okay, the numerator, plugging in each of those actually means taking those values of 1 and -2 and putting them into the function. And the function was x squared. So what we really have is 1 squared minus -2 squared on top. And then we have 1 minus a -2 or plus 2 on bottom. So 1 squared is 1, -2 squared is 4. So this is 1 minus 4 on bottom, and it's, I'm sorry, on top, and 3 on bottom. So what do we get? This is -1. So what we're supposed to do with these then is we're supposed to take each of these, in fact this is more accurate, and this, and set them equal to each other and solve. So see, we didn't have to do this entire right-hand side in Rolle's theorem, right? Because it was 0. So this is a little bit more work because we have to find this ratio. Not a lot more work, and it's not even calculus work, but it is a little more work. So we're setting each of these 2c equal to the other one, which was -1. And what would c equal? -1/2. And what we want to confirm is that that value that we got for c is in fact between the endpoints we were given. And is it? Yes, it is between -2 and 1. Just like before, if we got 2 values or 3 values or 4 values and some of them are and some of them aren't, we need to make sure that we're only specifying the ones that are between the values of our endpoints. All right, any questions on that? All right, surely we have another one of these, right? Oh, we do. Wonder of all wonders. Okay. What do you notice as we attempt this one in terms of continuity and differentiability? Yeah, there's an x in a denominator, which means we can't say it works because it's a polynomial because it's not a polynomial, correct? There is a place where this function is not continuous and not differentiable. What is it, Dawson?
0.
Yeah, at x equals 0. Okay, so this is not continuous and not differentiable. These two fail at x equals 0. Correct? So if this is the problem, as it's given exactly stated this way, what do we need to do next? Yeah, the mean value theorem does not apply. Does not apply. That's not DNA like your blood. Okay, does not apply. Doesn't work. Okay, but what happens, or what would we do the interval were 1 to 4 instead of -1 to 4?
Then we might solve.
Then it would work, right? Okay, so let's actually try it for this particular perspective as well so you can see what that would look like. What I want you to see is that the fact that something is not continuous or not differentiable at a particular point doesn't necessarily make everything fall apart. It depends on the interval you're working with. The original interval, it falls apart because that x value is between my endpoints. But if I have a different interval on this particular problem, I can still work the problem. So I'm not changing the problem. I'm really not. I just want you to understand that if the problem had been set up differently, I would keep going. So now I'm sort of changing the parameters of the problem so that we can see how the problem would work out if the parameters were different to begin with, okay? Okay, so we still have the same function. Let me write it down on this screen. 5 minus 4 over x. And now the interval I'm going to consider is not -1 to 4, but 1 to 4. So how about this one? Is it continuous and differentiable?
Yes.
Yes. It's because the only continuity issue, continuity and differentiability. Yeah. Is that x equal to 0. And that 0 is not between 1 and 4. Okay, so we're good to go on this. All right, so if that's the case, then I should be able to take the derivative, and I should be able to calculate the slope. So let's do the derivative, keeping in mind that this is probably more easily done if I recognize it as 5 minus 4 to the x minus 1. Okay, so what's the derivative of the 5? 0. What's the derivative of the 4 over the x, or the -4x to the -1?
Plus 4x.
Yeah, 4x to the -2. There's a negative there. Or you could recognize that this is 4x squared. 4 over x squared. What's that?
Oh, wait.
Yeah, it canceled with the other negative we pulled down. If you want to put c in there instead of x, more power to you. It doesn't bother me if you want to do that, but it's not really necessary. So I'm going to leave it like this. The other side of the equation is to take the two endpoints. So f of 4 minus f of 1 over 4 minus 1. Okie dokie. So f of 4 means to take the number 4 and to plug it into this equation. So 5 minus 4 over 4 is minus. And then to plug in the number 1, which is 5 minus 4 over 1. And this is all over 3. So what is 5 minus 4 over 4? That's 4. And what is 5 minus 4 over 1? 1. We get lots of 4s and 1s on this for some reason. And this ends up giving me 3 over 3, which is 1. So we have a slope of 1. So we should be able to take our equation from the derivative part, which was 4 over x squared, or 4 over c squared, and set it equal to that 1. Right, this is our goal right here. This is what the mean value theorem says I'm going to be able to calculate. How would I calculate this? What would you do? Yeah, I'd multiply the x squared. That would be my step. So this is 4 equals x squared. And this is actually technically x equals plus or minus 2. Yeah, but our c value, if we want to call it c, is only the 2 because that's the only one that's between 1 and 4. Now, it's important for you to realize that if you had not recognized over here that this failed, you might still move forward and try to calculate this thing, and it might actually give you values, and you might actually think you have found something, and you didn't actually find something that was useful, right? So it's not a matter of can I not calculate it. Sometimes you can actually calculate the values that you think you're supposed to find. It's just that the values you're finding are not actually answering the question that you thought you were answering. Bryson?
Can we just stop at the did not apply?
Yes.
Works? We don't have to.
Yeah, there's nothing else to do. Yeah, this problem as is would have stopped here. Katie?
Would there be such a question that it'd be similar to the one that we just did, where it would say, if it does not apply, find an interval that it would work?
I don't think that it would. I don't know that WebAssign could do it that way, first of all, because the interval you find and the interval that Chad finds could be both valid and completely different answers, and that would be very difficult for the programmer, I think, to make that work. Could you set it up where it was more like what I did, where it said, does it apply on this interval, does it apply on this interval? Yeah, that's a possibility.
Okay, so we could possibly have a single equation and given different intervals.
Sure, that's a possibility. Mm-hmm.
So you could have an equation that's not continuous and that's not differentiable, but if it's just continuous and differentiable within the interval.
Exactly. Exactly.
Okay.
Yeah, so if you think about like finding where this is not continuous, not differentiable, we've done that, right? We've looked at where things are not continuous and not differentiable sort of on the whole number line. And then you just have to figure out if the points where it has these problems, are actually within your interval. Exactly. All right.